All right. Well, thank you, Luis. Thanks for the invitation. It's a pleasure to be here. And yeah, so local theta correspondence and C-star algebras. I believe theta correspondence is very familiar to this audience, and C-star algebras are probably not much. But yeah, I won't get into the really technicalities of C-star world. We're gonna be thinking of really C-star algebra. At least the ones that we will use are gonna be kind of buffed up versions of group algebras, kind of. But yeah, so before I start, this is joint work with Bram Mesland, and let me make an introduction. So it's local theta correspondence, not really the global that I'm talking about. I guess perhaps a lot of you probably are more familiar or interested in automorphic forms and where we use the global theta correspondence, but this is kind of the building block. So in a nutshell, what's going on? So let's remember the local theta correspondence, or also known as Howe duality, local theta correspondence. My daughters have just came back from school, so there might be some noise in the background. Apologies. Right, so we have, what do we have? So we have a suitable pair of reductive dual pair. So this is two reductive groups. So the point, so this is a configuration of these two groups. They sit inside an ambient symplectic group, and they are each other's centralizers. This is centralizers, the dual pair formalism introduced by Roger Howe. And what we do is, so the example, of course, the classical example is you take SL2 and, well, maybe I should fix my local field of characteristic 0, F. So reals, complex numbers of an extension of QP. You can maybe, the most classical pair, I guess, orthosymplectic pair. You take SL2R as one of the groups, and the other will be some kind of orthogonal group. And what we do is, so the setup is that, so you have these two groups sitting nicely inside an ambient symplectic group, and the symplectic group has this magic representation. So there is a projective representation which factors through this metaplectic double cover into some endomorphisms of some, let's say, Schwartz space. This is the so-called oscillator representation, or the Weyl representation. And what we want to do is, so this is a cover of the symplectic group. It's a very distinguished representation. It's minimal in some sense, quite big, but not terribly big. That's important for the theory. And we want our group G cross H. In many cases, there is a splitting, studied by Kudla, so that we can pull back the oscillator representation to a representation of G cross H. There is one case that we cannot pull when P plus Q, for example. There's an exceptional situation where G has to be replaced by its double cover. We will talk about that, as probably you are all familiar with that. When P plus Q is odd, you cannot keep SL2. You have to go to the metaplectic cover. But let's not worry about that, though. General, the big picture is that, so we have distinguished representation of G cross H. And the Howe duality, or local theta correspondence, can be described very easily. Once you have this oscillator representation split, so that's you see it as a representation of G cross H. The idea is like it's a branching problem. You want to decompose this representation of the ambient big group as a G cross H representation. You want to basically decompose it. And the recipe, it was conjectured by Howe and then proven by Howe, Waltz, Perget, other people, we take guns, but now it's a theorem, is that, so you look at the duals, admissible duals of the two groups. So these are, I'm looking at working in the admissible category. These are admissible duals. So this is a large category that contains all the unitary representations, but it's enlarged with the idea that it allows us to control things algebraically, studied algebraically. So if F is non-Archimedean, this is the same as the category of GK modules. I meant Archimedean, not Archimedean. And if F is non-Archimedean, which probably I will focus on this today, then this is the same as the irreducible admissible guys are just the smooth irreducible guys, so that stabilizers of points are open. And that's the same as the modules of the Hecke algebra. This category is the same as the Hecke algebra modules. This admissible category, Hecke algebra modules. So it makes it quite algebraic category. So, so we look at these two categories of duals, admissible duals of the two groups, and we come up with this very simple recipe. We say that, let's say, take pi in one and sigma in the other. We say that pi is in correspondence with the sigma from the other side, or we say that, or theta lift of one is the other. If and only if there is a non-trivial intertwiner from this oscillator representation, this is our big representation, big but not too big, onto the product. I think I should change the order because I put G first. I think pi goes first, pi tensor sigma. So this is the recipe, and it's known that actually if this intertwiner space is non-trivial, it's one-dimensional. So there's a kind of a multiplicity one situation that tells us that the oscillator representation is very big, but not too big. So that kind of makes this all work. So the theorem is that this rule defines a bijection between subsets of the duals, admissible duals, between certain subsets of the admissible duals on the two sides. Right. It's just this. This is the caricature. We have here of G, here's of H, and we have some bijection between certain parts of these. Maybe we don't need to give a name to these subsets, but I might use this terminology much later. Yes, that's all there is. Of course, this is just the beginning of a story, right? And you want to ask them, okay, who enters the theta correspondence? Can you describe it to me? What are these subsets that are in bijection? And if a pi enters the bijection, can you describe what it goes to? Describe in what sense? I don't know, maybe Laplace parameters or something. So there is, of course, this kind of basic question kept people thinking about all this kind of stuff for a long time. And of course, globally speaking, what you can do is that if you have these groups then defined globally, dual pair, then you take an automorphic representation on one side, automorphic representation. You decompose it into local pieces, such that so these pieces lie in the local components, representation of the local components of the group, GQP, and then you then apply, if you apply the local theta correspondence to the local pieces, this almost unramified everywhere, right? And the unramification is preserved, so these local images will be, almost all of them will be unramified, so I can bundle them. And this now is a representation of the other guy. And it can be shown that this is an automorphic representation if it's non-zero, GQ, HA. And if you were to think of, if you take an automorphic form, from this automorphic representation and do the, the more classical theta lifting with this theta kernel and get an automorphic form for the other group, and then, change the automorphic form and look at the automorphic representation, you would get, it will be compatible with the theta kernel lifting type of thing. So this is what we call the global theta lift of the automorphic representation. So this is a local global is compatible with the automorphic so theta kernel kind of lifting that we do maybe more hands-on on the level of automorphic forms. Of course, that kind of lifting maybe has more extensions into, you can regularize if it doesn't converge. There are various extensions of that kind of way of doing theta lifting. But this is more at the classical level, more of representation theoretic way of looking at theta correspondence. I will not be really looking at the global aspect, so this is a local talk, I'm afraid, but hopefully it will be entertaining enough. Right, so this is local theta correspondence. It relates to global theta correspondence that we all love. Now, what's the point of this talk? Well, we're going to look at this bijection here that's described with this branching rule, so to say, of the breaking up the oscillator representation into pieces. We're going to look at it from a kind of ring theoretic perspective. So, okay, what do I mean? So that's a ring theoretic perspective. So I'm going to take a look at this bijection, interpret it in a different way, looking at from, instead of looking at group representations, I'll be thinking about modules for the group algebra. So switch to a ring theoretic module perspective. So the basic example, so let's think of this to motivate the situations. Let's say RS are rings, maybe unital to be on the safe side. And you take a bimodule. So you take a module X vector space where Rx on the left, R left action, left R action, and let's say S X on the right, and these actions commute. So this is what we call, I guess, RS bimodule. So given such a bimodule, we can have this very simple functor. I'm going to call it induction functor, and you'll see why. I'll try to justify why I'm calling it induction functor. It goes from S modules over S, the ring S, to modules over R. It's very simple-minded construction. So let's say if you have a module, let's say V, you send it to the balanced tensor product of, not S, S is reserved for the oscillator representation, X tensor V, but we're going to balance it over the ring S. So what does this mean? Maybe I'll need a new page. How do I do this? Like this? Yeah. I should number my pages. I guess this is 3, this is 4. So what is this, by the way? Is this balanced tensor product? It's, you take the usual tensor product, and what I'm going to do is X hit from the right by S tensor V. I'm going to view it as the same. So I want to transfer the S action from the two components. So I'm going to be cautioned out by these differences. Space spanned by this difference. So X in X, V in V, S in the balancing ring S. So this is the construction. This is the balanced tensor product. It's an algebraic construction. I'm going to define it. So this is defined this way. And remember that X admits an action from the left by R. So this is an R module. How does R act? R acting on X tensor V is simply defined to be Rx tensor V. And then because the action of R and S commute, this action descends down to the quotient, so that this balanced tensor product becomes an R module. And this is a simple functor that goes from category of modules on one ring to the other by this balanced tensor product construction. And I call this kind of induction functor due to the basic example. This example goes back to actually, I guess, 50s, but so think of two groups, H and G, finite groups, one inside the other, one subgroup of the other, finite groups. And then you can look at the modules for the small guy and go to the modules for the big guy, the group algebra of the big guy. And I'm going to do this. So take V, let's say take a representation of H and view it as a module over the group algebra. I'm going to send it to take the group algebra of the big guy, and I'm going to view it as a group algebra of the small guy from the right by hitting it from the right. And I'm going to see it as a bimodule by its own regular action coming from the left. So this is a bimodule for the two algebras. And I'm going to be I'm going to use this as my bimodule. So I'm going to simply take the balanced tensor product of the group algebra of the big group as a module over the small group algebra of the small guy. And I'm going to take this balanced tensor product. So this is just base change, really. I'm doing base change here. And the action of group algebra of the big is in the usual, from the first component as we described above. And so you can actually show that this is nothing but the induction of the representation of pi from H to G viewed as a module over the group algebra of the big guy. So induction in the sense of Frobenius and or going, I guess, in the finite group case, can be captured at the ring level by this kind of bimodule functor. And more generally, you can, if you can find more general bimodules, you can cook up this kind of functor. So I want to look at theta correspondence from this kind of perspective. Now, okay, what are the rings? Oh, so let's go back to theta correspondence. Okay, 5. So let's stick to, for convenience, F non-Archimedean. So remember, so we're having we have a dual pair, and we have a map operating in some subsets of the two admissible duals. And I mentioned this in passing, but this is the same as the Heck algebra modules of the. So this category, admissible category, is the same as smooth representations. It's the same as Heck modules, modules of the Heck algebra. So let's stick to the Heck algebras as our rings. So here, remember, so these are compactly supported, locally constant functions on the group, and they are ring on the convolution. And so you ask yourself, okay, so let's take a representation, admissible representation on one side, and send it to the other side. So what I'm going to use, of course, what's the bimodule here? It's the oscillator representation. So I'm going to see the oscillator representation as a bimodule over the Heck algebras. And what I'm going to do then, I'm going to take an admissible representation of the group, let's say H, and I'm going to do the balanced tensor product over the Heck algebra of H. And this is going to give me a module for the other Heck algebra because of this acting on S from the left. And you can ask yourself, what is this? This I can now actually, as of 2 months now, that's a result, very recent result of Locke and Pshebinda, two theta correspondence experts. It's just 2 months old or something like that. They just announced that actually this balanced tensor product here gives you the so-called big theta lift of pi gradient. If you haven't, yeah, so this is the so-called big theta lift. So this is a kind of a approximation to the theta lift, which sometimes is known as small theta lift. So you can, this is kind of the pi isotopic, maximal pi isotopic quotient of the oscillator representation. And the small theta that we know, that I mentioned earlier, is the maximal irreducible quotient of this guy. but you can say that it's a proxy. It's a very good proxy to the theta lift, the big theta. It's a proxy to the small theta. Sometimes I didn't use the word small theta, but yeah, theta lift. I mean, this actual result was inspired by, well, by the result I'm going to talk about now, our result. So I was very happy to see that it inspired the experts, theta correspondence experts, to get some new things out. But what we want to do, okay, I'm going to talk about a similar construction where I'm going to do a balanced tensor product, but I'm going to capture the little theta itself. Well, okay, so today, so I'm going to use the so-called theory of C-star algebras, and especially, I guess, in this setup, I'm going to you're going to boost up the Hecke algebra to a C-star algebra. Now, we do not need to go into the whole theory of C-star algebras because it's going to be a very concrete construction, but this is a very small, it's a category of, special category of class of involutive Banach algebras, satisfying a very small, innocent-looking identity, but it makes them, turns them into a very rigid class of involutive Banach algebras with beautiful properties. But what we're going to do is this: take your Hecke algebra. So I'm going to do a completion. Here's how am I going to complete this Hecke algebra. So look at the regular representation. So remember, this is compact supported locally constant functions on H, right? So as such, you can act on L2 of H via convolution. So they act on L2 of H as a convolution operator. So there's a map from this Hecke algebra into the algebra of bounded operators on L2H. And just look at the image. The image sits as a subalgebra here on the right-hand side. And take the norm closure with respect to operator norm. Closure with respect to of the image with respect to operator norm. So that gives me a C-star algebra. It's an algebra of operators. It's an involutive Banach algebra satisfying a very special property. Its special property is this, actually. It's very easy to state. The norm of A star is the same as norm of A squared. So it's called a C-star identity. So this is satisfied when you take this closure. And that's all what I'm doing. So I'm taking a certain completion of the Hecke algebra. And it turns out that when you do this, you land into the world of C-star algebras, which is great. C-star algebras are very nice objects. But you enlarge the Hecke algebra, and that there's a price to pay off. Remember that the Hecke algebra was seeing all the admissible representations, admissible dual was controlled by the Hecke algebra. When you boost it up to the this closure, I didn't give it a name, but the name is the so-called reduced C-star algebra of H. R for reduced because I used a very specific representation. It's called the regular representation. If you extend your extend your Hecke algebra to this bigger algebra, C-star algebra, you lose a big chunk of the admissible dual. So you now only see tempered representations. Remember, tempered representations are certain, it's a subclass of unitary representations singled out by they are weakly contained in the regular representation of the group. Or you could also characterize it as its matrix coefficients live in L2 plus epsilon. They're almost L2. There are different ways of describing temperedness, but it's a very special class of unitary representations. And this completion of the Hecke algebra sees those guys. So tempered dual, you can say that as modules over the reduced group C-star algebra. So C-star H mod modules I'll put it this way, tempered dual of H. Right. So now what my goal is now to do something like this. I want to use now the oscillator representation, want to view it as a module over the group C-star algebra, reduced group C-star algebras of the two groups. And because these representations only see tempered representations, so I hope to get kind of a transfer between the tempered dual of one guy to the tempered dual of the other guy. But this is asking too much. You know, how do we know that temperedness is preserved under theta correspondence, local theta correspondence? And in general, it's not preserved. So this is something very special. But it turns out that it does happen. So there are, let me, this is 6. Let's open 7. It turns out that, I mean, if you hope that something like mechanism like this will work, you need to make sure that temperedness is preserved. We need to get started, even to have a hope that this will work. We need to have that, it's not a great sentence, I guess, temperedness is preserved. So this is a very sweet condition. And it turns out that so if this is called, brings us to the so-called equal rank case. So it's a fact. I guess the classical part goes back to Waltz-Purger, and the generalizations go back to Savin and Gunn and Savin. When G and H dual pair are of equal rank, now I'm not quite defining, but remember, so these are all isometric groups of vector spaces with symmetric, skew-symmetric kind of forms. So I'm talking about the size of the underlying vector spaces really, are equal rank. Then theta correspondence, or how duality preserves temperedness. So the examples we will think of are metaplectic group 2n and odd orthogonal group 2n plus 1. This is also known as Shimura-Waltz-Purger correspondence. If n is 1, this is the Shimura correspondence going from, you have, I guess, O21 is, SL2, so you go from classical modular forms to half integral weight modular forms kind of situation, and its generalizations like this. Or you can, if you work with unitary situation, both we have vector spaces, Hermitian vector space of the same dimension. We have, skew symmetric form on one and symmetric form on the other one. So these are the pairs that I'll be really thinking of. Probably quaternionic pairs also work, but because I'll be needing facts from literature, and those facts I couldn't, so probably also quaternionic equal rank pairs also work, but let's just stick to these guys. And in fact, so I mean, there is also almost equal rank pairs that are very, and the general, I guess, principle is that when the groups are very similar in size, almost equal or equal rank, theta correspondence turns out to be a functorial in the sense of long lengths, and then you expect great things to happen, transfer of a lot of information, preserving of, for example, temperedness is preserved. This is what I'm going to be starting with. But in fact, discrete series go to discrete series, and you can, it's known, for example, goes back to Gunn and Ichino, formal dimensions. You can normalize the Haar measure so that formal dimensions of the discrete series that are matching with each other also are equal to each other. You can talk about, if you take the distributional character of the one representation and look at, you can relate it to the character of the guy that it goes to under equal rank theta correspondence. So there's a lot of transfer of information because it's a Langlands type of functoriality, like in Jacques Langlands correspondence. There's a lot of information flow. But yeah, so temperedness is preserved. And so the theorem, basically what we prove in this setup, let me just at least put a statement of a theorem. This talk I've given many times to various different audiences, so that catering to their backgrounds, and several times I've done a horrible job of not finishing on time, and stuff. But hopefully it's gonna go better today. We'll see. Right. So F non-Archimedean. You at least put a statement. Non-Archimedean. GH equal rank pair. One of the two that I just listed here, kind of pair. And what else do I want? Yes. So then we can construct a C star bimodule. So I'm going to say a C star bimodule because it's much more rich object than an algebraic bimodule of two rings that we just discussed. It needs a lot of extra structure. A C star bimodule, maybe X, for the reduced group C star algebras of the two groups in question, constructed from the oscillator representation. So I essentially take the smooth oscillator representation, the Schwartz space that these guys act on, and I do a completion, certain completion. That's because I'm using C-star algebras. It's a little bit more complicated, but we can construct a C-star bimodule such that now there is an induction functor that you can now construct, goes from the tempered dual of one to the tempered dual of the other, such that if, say, so it goes like this, I guess, it's the balancing functor. So I take this X and do a balanced tensor product over the reduced group C-star algebra and send it here. Now this even here, the balancing tensor product needs to be done with a little bit over the top of the algebraic balancing act. You need to do some kind of completion, so there's a little bit more involved, but such that this induction functor captures theta correspondence, or theta lifting, let me say it for short, i.e. if so this guy, this G module that I have on the other hand side, it's a tempered representation of G because this is the same category. It's going to be isomorphic to the theta lift, small theta I'm talking about, not the big one. Well, it's isomorphic in this case. Anyway, of the gradient, contragradient of pi. Indeed, if the theta lift is zero, in other words, if theta doesn't enter the theta correspondence, then this module, this quotient is really trivial. But if it does enter the theta correspondence, then this module that I cook up on the other hand side is isomorphic to the theta lift of the contragradient of pi. So in that sense, it captures. And so this is the first thing. So so basically it says that tempered, in short, tempered equal rank theta correspondence. So I'm only looking at the tempered part, because, remember, so this is something's going on at the level of the whole admissible duals. So, some part is matched in bijection with some part, but I'm only interested in the tempered guys here, because I'm using this, let's say this is the tempered dual sitting inside the admissible dual. So I'm only looking at tempered guys that enter the theta correspondence here, this intersection here. So when I say tempered equal rank correspondence, I'm talking about the tempered parts here. So this is captured captured as an induction functor for reduced group C-star algebras. Now, if you're working with local theta correspondence, you can ask, okay, why should I care about this? I will give some applications, but at this generality, well, it's a functor. It's a different way of looking at it that wasn't perhaps observed before. But also I can say immediately that a lot of people are not interested, but these, there is these duals come with a topology on it. Lots of people maybe just want to look at the maybe Poincare measure as a measure space, but actually these tempered duals, I mean, there is a nice even the whole unitary dual. They have they come equipped with the so-called Fell topology. They have natural topologies on them. You can maybe see this is convergence of matrix coefficients on compactor. You cannot describe it that way through matrix coefficients. These are so-called Fell topologies. And it is known that this induction functor at the level of C-star algebras is continuous. So induction functor for a C-star bimodule is a continuous functor with respect to this is continuous. Continuous is a continuous functor, and this is a general fact from this C-star algebra bimodules. Duals representation space of C-star algebras have this nice topology and is continuous, this kind of functor. So we see that theta correspondence is continuous, meaning that this is actually it's a homeomorphism. If you care about the topologies, that also gives you extra information. It's a homeomorphism. But you can, if you want to really perhaps get some representation theory, maybe some results that representation theorists are maybe working local theta correspondist or cares about, then let me describe you maybe two applications, some applications. For the applications, well, maybe before the applications, I should at least, how much time do I have? Maybe, okay. I should say that there is a, here. So maybe maybe the remark, what do you have to do to prove something like this? So what I want is you take the Schwartz, the oscillator representation. So this is the smooth oscillator representation. So it's some kind of Schwartz space, right? Smooth oscillator representation, affording the fresher space, oscillator rep. I want to view this as a C-star bimodule over these C-star algebras. And even to get going, you need to, first of all, these group C-star algebras, remember, so if you're a module for the reduced group C-star algebra, you have to be a tempered representation of the group. So these oscillator representations for G and H, they need to be tempered. So you need information about the growth of matrix coefficients of this oscillator representation, and these things are in the literature. So we are using a lot of facts about oscillator representation from literature to build this up. So that's so this is a tempered representation so that the reduced group C-star algebras act, but also it's not just a bimodule in the algebraic sense of rings. You need to really equip this with extra structures, so that what you need is you need a Hermitian form that lands inside the C-star algebra. So what you want, basically you want to imitate, there's this idea, if you take a Hilbert space, it's a module over complex numbers, and the Hermitian form that exists on the vector space, it's valued in the complex numbers, right? But complex numbers is a kind of trivial C-star algebra. So replace the complex numbers by a C-star algebra so that you have a module over the C-star algebra. But now you want an inner product that lands in that C-star algebra. And C-star algebras have an intrinsic notion of positivity. So you want a positive definite inner product landing in the C-star algebra, and that you need to construct that, and we use matrix coefficients for that. And again, results about growth of matrix coefficients say that the matrix coefficients of the oscillator representation for the smaller group always lands in the Harish-Chandra-Schwartz algebra of the group. That's the general fact. And here, because the two groups are equal rank in both sides, from both sides, the matrix coefficients land in the Harish-Chandra-Schwarz algebra. I'm not writing things down. I'm just talking too much because it's going to take too long to write things in. But to say, yeah, so you take the matrix coefficients and they land in the Harish-Chandra-Schwarz algebra of the group. And this turns out to be a dense subalgebra of the reduced group sister algebra. These are very fast decay. Okay, maybe I won't define the Harish-Chandra-Schwarz algebra, but so it's really the saying that the matrix coefficients have a very fast decay for the small group, and because it's equal rank for both sides. And then you need to show positivity, and you have to use a lot of structural theory from doubling zeta integrals, its properties, dichotomy principle, things like that. But let me move on to this application I mentioned for maybe more really representation theoretic application. For that, we move on to, with more work, you can establish a Morita equivalence. Now, Morita equivalence is a notion coming from ring theory. If these two rings you have, they have their category representations are isomorphic, then it's called Morita equivalent. And what we have is a C-star version of that. So you have this smooth oscillator representation, and you're taking matrix coefficients with respect to, let's say as a H representation. And these guys then live inside the Schwarz algebra of the one group H, which is a dense subalgebra of the reduced group C-star algebra. And you can also take matrix coefficient as a G representation, and those will live in the Schwarz algebra of the other group against a symmetric situation. So because of equal rank, live inside the reduced group C-star algebra of G. Now, these matrix coefficients, they land inside your Schwarz algebra, but they don't span the whole Schwarz algebra, because that would mean that all your tempered representations enter the theta correspondence, and they don't. Roughly speaking, half enter. So these matrix coefficients span. You take the span of that. That's an ideal. Let me call it I. It's an ideal that lives inside your. It's a two-sided ideal in your group C-star algebra, and they are in particular also sub-C-star algebras. And also you take the span of these matrix coefficients from the H side, and they span an ideal. And this, again, is in particular sub-C-star algebra on the other side. And with extra work, so this is actually quite intrinsic. So yeah, okay, maybe theorem part 2 or something. I and J are Morita equivalent. What does that mean? So it means that the induction functor X going from spectrum of I to spectrum of J is an invertible functor, invertible. And here the spectrum of I is precisely those tempered representations that enter theta correspondence. So I don't know how to write that, maybe like this, tempered sub theta of G, and this is tempered sub theta of H. So the representations, the irreducible representations of these ideals, so we kind of cut down the reduced group C-star algebras and thrown out all the tempered representations that do not enter the theta correspondence, so that we are working with these smaller subalgebras, ideals, and we show that they are in Morita equivalence. So the bimodule, C-star bimodule that we cook up from the oscillator representation is an invertible functor going between the reduced representations categories of these two algebras. And there's the crucial input here, which probably I wouldn't have managed to do it if I was in touch with Vitek Gan, and he mentioned the result of his that looked like that could be used for this purpose. It's a local Rallis product. You know, the Rallis inner product formula, the global one relating the norms, Pearson norms on the two sides. There's a local version of that by Gan and Ichino, local Rallis inner product formula. And it turned out that that's precisely what was needed to show this. It was very interesting. It's a very interesting result, how it really just fit the shoe just like that, and it worked. And okay, so maybe I should wrap this up, right? 50 minutes now. Yeah, is that right? Yeah, I'm gonna wrap it up. Okay, so Morita equivalence is a
sorry, Haluk, you can go a little bit longer.
Okay,
like.
all right, maybe 5 more minutes or something. Okay. Morita equivalence is a very strong condition if two, rings, well, I mean, their representation theory essentially is the same. That's what you're saying. And you can expect then a lot of flow of information, which is compatible with what you observe in equal rank theta correspondence. And indeed, we can explain some of that and maybe show new results. For example, application 1, once you know that they're in Morita equivalence, these ideals, application 1, you can do this. Transfer of characters. Let me just label it this way, transfer of characters. This kind of stuff is quite useful. I mean, for global purposes as well, like in Jacques-Langlands transfer. So, okay, what am I talking about? So let's say pi in H tempered. Take a tempered representation, irreducible representation on one side. Now, character of a representation of a finite group, it's you can generalize that, and you have this for reductive groups. You have this distributional character of Harishchandra. So if you take compact support test, if you take a test function, you can look at test function f. You can look at pi of f, and that's a trace class operator. And then you can look at this trace. It's a well-defined trace. You take a number. So it's a distribution. But for tempered guys, that's kind of where the name tempered, I guess, comes from. You can extend this to the Harishchandra-Schwarz algebra. So this is again space of fast decay functions that contains these space of test functions. You can extend it to here. You can extend so that you have a tempered distribution. Now the character is a tempered distribution, and the result is that, or application is that, now take two vectors in the Schwarz space. This is the oscillator representation, two smooth vectors in the oscillator representation. Remember that we use these matrix coefficients to go down into the reduced group sister algebras, or the Schwarz, Harishchandra-Schwarz algebras that are dense inside the reduced group sister algebras. So if you look at x, y, let's say h. So I take the matrix coefficient associated to these two vectors. Remember, maybe I never wrote this down, assuming that everyone understands matrix coefficient, but it is what you think it is, right? So you take yeah, you act on one of the vectors by H group element in the oscillator representation, and then you take the inner product with respect to the L2, because the Schwarz space is inside an L2 space, right? The oscillator representation, you take the norm, the inner product. So this gives you a number, so it's a function on H to C, and you can show that this lives in the Schwarz algebra, this effect. So I take this Schwarz function, so this guy belongs into the Schwarz algebra of H, and so if I take the character of that distributional character, the result is that this is going to be the same as the distributional character of the theta lift of pi, or pi star, or actually you can get rid of pi contra gradient by Medley, of yxg. So remember, this is a G representation, tempered G rep. And this guy, the matrix coefficient for yx, it's changed the order slightly because there's a contra gradient involved. So this is going to live in the Schwarz algebra of the other group. And so this is directly relates the distributional characters of the two representations that are tempered representations that are in theta correspondence with each other. So this is really comes out very quickly in half a page proof once you know Morita equivalence, the general fact that they're Morita equivalent, so you can show this very easily. And I'm putting it as a theorem. It has been announced by Vitek Gunn. Announced this, I should mention that announced this already a couple of years ago. He explained some how to prove this in some talks, online talks. There are some recordings on YouTube. Our proof is different, of course. We use C-star algebra and stuff, but this result exists. Maybe not in print, but on an online announcement. And so this is one thing. So these kind of results have been people pursued in, for example, in stable range when one group is much bigger than the other. Tomasz Przebinda has pursued for explicit description of how to describe the distributional character of the theta lift of one guy in terms of the character of the original guy and stuff like that. So it's a very interesting question for if you're a specialist in theta correspondence. And another application, which I quite like because it uses K-theory of C-star algebras. So it uses some cohomological techniques. Application 2, I should say. We are reproving. I'll mention it when I state it. Okay, so preservation of formal degrees, I should say, as a small short title, preservation of formal degrees. Now, I did mention that in the equal rank case, if your pi is discrete series, then its theta lift is also a discrete series. And then, discrete series have these formal degrees or formal dimensions. If pi is a discrete series representation, let's say, okay, let's start with, let's say, H side discrete series. You can think of this as just a sub-representation of the regular representation. So it's contained in the regular representation. Or if you want, from a topological point of view, or from a Palancherel measure, so this is the measure of these guys in the Palancherel measure will be positive. So they're atomic pieces of the Palancherel measure, or topologically speaking, they're gonna be isolated in the unitary dual, isolated points in the unitary dual. Yeah, so discrete series that we are, I guess, all familiar with from classical Caspital modular forms. So take a discrete series, then it's known that its theta lift is also a discrete series on the other side. And it's a fact shown by, I think, Gunn and Ichino in their, one Invenciones paper about some formal degree conjecture. They show that the formal dimension of pi is going to be equal to the formal dimension of its theta lift. Of course, the formal dimension is well defined up to Haar, up to scaling. So you need to really, it depends on the chosen Haar measure. But they're basically saying that there is a normalization of Haar measures where you have this equality for every pi. And you can show this again in a fairly, well, I mean, the way you show this is not novel to C-star algebras. It's a well-known technique in C-star algebras. So what you can do is this. So there is a cohomology theory of C-star algebras. It's really inspired by topological K-theory. So what you do is you just look at the projective modules over your C-star algebra. If you look at vector bundles over your compact space, right, and look at the topological K-theory of those, well, if you look at the module of sections of that vector bundle, it's going to be a projective module over the C-star algebra of continuous functions of the space X. So that's how you pass from vector bundles to projective modules over rings. So there's a K-theory working wonderfully for C-star algebras. And what you can do is that when you have this kind of Morita equivalence, you have a map that established by this bimodule that I mentioned, the Morita equivalence bimodule, at the level of C-star algebras. Technically speaking, I should put not the full ones, but the ideals that are in Morita equivalence. But anyways, so what you can do is that if pi is a discrete series for H, then it's going to be an isolated space, isolated point in the unitary dual. It's a closed open Klopen point. And that kind of point gives you a generator for the K-theory. And this applying this map of, so these are abelian groups, and the map linear homomorphism applied by the induction, this bimodule X. Remember, this is nothing but the theta lift of pi contra gradient. I know that that's also a discrete series, so that's also going to give me a generator of the K-theory on the other hand side. Okay, so far nothing too fancy. I mean, this is our well-known things on the group C-star algebra side of things. Now, the nice thing is that there is a trace map on the K-theory of group C-star algebra, since by evaluation at identity. So if you take a f, let's say in compactly supported function in H, or in the Schwarz algebra, so this is a subalgebra of the group C-star algebra, and simply you evaluate it at the identity element. That gives you a trace function tau, that's called a canonical trace, and it's going to go to, I guess, complex numbers. Actually, you can show this lands in the real numbers. But so the fact is that the canonical trace of the class of a discrete series is nothing but the formal dimension of the discrete series. You can also see this if you look at the potential measure, some kind of basic harmonic analysis. The evaluation at identity really picks up that potential measure for the discrete series. So you just use this fact and argue that this is also well known. I guess it's well known in the C-star algebra side of things. So if you have a trace on your C-star algebra, and if you have a Morita equivalent C-star algebra, then you can transfer that trace to another trace function on the other C-star algebra. And for the canonical trace, we show that the transferred trace is also the canonical trace on the other group C-star algebra, so that the values which picks up the formal dimensions are equal. That's I'll yeah. So it's in a nutshell. So we use this cohomological setup and the fact that these transfer of traces under Morita equivalent C-star algebras, and that the canonical trace evaluation at identity picking up the formal dimension to show that the formal dimensions are preserved. As I said, this is known. Gananichino proved this in 2014, but we prove it in a very different way. Okay, I'll stop here. I guess it's a lot of storytelling now. I should probably stop. Thank you for listening.